There is something mesmerizing about fluids. The fact that they can even be rendered on a computer is just insane to me. Smoke curling through the air and colorful swirls of liquid that look chaotic and yet still hold beauty. And I thought to myself, how? Just how? So I decided, what better way to learn about fluid simulations than to create one myself. Now, this sounds really cool and all, but I had no idea what I was getting myself into. Creating my own fluid simulation almost broke me. So ladies and gentlemen, I present to you my journey of creating a fluid simulation from scratch. Okay, so the logical first question to ask when making something like this is, how does it work? At first, I thought the answer could be pretty straightforward, maybe just a few math equations and some lines of code, and boom, I would have a fluid simulation. Oh boy, was I wrong. As it turns out, fluidical motion is governed by an equation called the Navier-Stokes equation. Each part of this equation represents the physical properties of a fluid: motion, pressure, diffusion, and any external forces. This single equation dictates how fluids move, and this is our key to a fluid simulation. Now, obviously, I wasn't about to solve this equation perfectly, and frankly, I don't think I have the skills to be able to. But, thankfully, in 1999, a researcher named Jos Stam introduced a method that made real-time fluid simulations possible. He published an amazing research paper called Stable Fluids that I religiously followed to make the simulation. So, the first step in making our simulation was to divide our screen into a grid. This is because a fluid simulation does not treat a fluid as one big entity. It divides it up into a collection of tiny cells. Each of these cells hold values about the fluid's density, pressure, and velocity. I created 3 different grids, one for the actual fluid and the other 2 for the x and y velocities respectively. Once I had the grids in place, I could move to the first part of the simulation: diffusion. Diffusion is what makes the water spread out. Right now, what we have is just a worse version of Microsoft Paint. The way that we can make our fluid, a fluid, is by making each cell share a little bit of its values with its surrounding cells. In code, the diffusion formula works by repeatedly averaging each cell with the ones around it. This function calculates how much fluid should spread to neighboring cells during each frame. And by running this over and over, the fluid slowly smooths itself out. This was genuinely groundbreaking for me, but the fluid felt very not like a fluid. And that's because I hadn't added the property of advection. Advection is actually what moves the fluid through space. Right now, our fluid is just blurring, not really moving anywhere. Now, since advection makes the fluids move, my initial thought was to add a force that pushes the fluid outward. But the way that advection actually works is very unintuitive. Instead of moving forward, each cell in the fluid looks backward. For every cell in the grid, the simulation asks, where did this fluid come from? And then it pulls fluid from that location into the current cell. Each cell looks at its current velocity and traces backward to figure out where the fluid should have come from. Since fluids can't exist outside of our grid, the values are clamped to make sure that everything stays within our simulation. And the most important part of advection is interpolation. Since the fluids will not land perfectly on a cell, the simulation has to blend values from nearby cells. This is what makes our simulation feel like a fluid. Now, you may notice that our fluid is rainbow. And even though this looks really cool, it's a bug, and I had attempted to fix this at this point, but I couldn't figure out how, and kind of just left it for now, because it does look cool. It's alright though, because we had more pressing issues to deal with. Issues like how I know you haven't subscribed right now. Issues like how the fluid could bunch up or disappear in very strange ways. And that's because our fluid right now is compressible. Real fluids are incompressible. Jos Stam explains this very well, and thankfully also gives a solution. The next major step was projection. To fix our fluid's ability to compress, we're going to add something called pressure into our simulation. It works pretty well, it does work well, but it also works pretty simply, as this force will just push the fluid outward whenever it starts to compress. First, the simulation measures how much the fluid is compressing at each point, and this tells us where the fluid is piling up or spreading out too quickly. Then it calculates a pressure value that will counteract said divergence. Finally, the velocity is adjusted under the pressure values to make the fluid believable and realistic. We have just created an incompressible fluid. Right now, our fluid is looking pretty nice, but it's still missing something. A real fluid would make swirls and intricate spinning patterns. To capture that, I needed to implement vorticity confinement. To recreate this behavior, we must detect where the fluid was spinning. In physics, this spinning motion is called vorticity. It measures how much a tiny region of fluid is rotating. First, we calculate something called curl, which tells us the strength of the rotation at each point in the fluid. Once the spinning regions in the fluid are detected, the simulation slightly pushes on them to strengthen the swirls. This process is called vorticity confinement. Adding vorticity confinement made the fluid look like it was dancing. It's incredible that this was made just from math. We can even add an obstacle to see how the fluid would interact with it. Alright, so at this point, we had a working fluid simulation. The fluid could flow, swirl, and even collide with obstacles. What started as a few numbers and a huge equation has now turned into something that feels alive. And honestly, it was worth the months of failure and crazy math and physics and all that. Thank you guys so much for watching this video. Let me know if I should make more simulations similar to this. Be sure to like and subscribe, and I will see you guys later.